different astrophysical areas, and today he's going to tell us about double diffusive convection with cross diffusion. So please, Edgar.
Thank you, David, for the introduction, and thank you, everybody, for coming to this talk. So this came about because of a contribution that I made to the KITP meeting earlier this year. And I think some of the organizers wanted to hear a little more about this topic. So my plan for today is to say a few words about why I'm interested in this problem. And then I'm going to spend a few minutes talking about a model problem, which is simpler to understand, the so-called Swift-Homburg equation.
Slide the arrows to work.
Sorry?
Okay, great, it works.
Can you hear me? Okay.
Yes.
So I'm going to say a few words about the so-called Swift-Homburg equation, which will inform allow us to interpret the results that I will talk about for a fluid problem, namely this double-diffusive convection with cross-diffusion. So this will turn out to be very useful for understanding the fluid problem. And I'm going to do two versions of the fluid problem. I'm going to talk first about double diffusive convection with this parameter S, which is called the separation ratio being negative. That's sometimes called the anomalous Sorey effect. And that will give rise to a variety of structures, which I will describe, including localized states. And I'm particularly interested in those, and we'll see that the localized states can move, and therefore they can collide, and we'll talk a little bit about that. And then I'll say a few words about the opposite problem, where this separation ratio S is positive, and that will actually allow us to derive the so-called conserved Swift-Homburg equation directly from the fluid equations. And then if there is time, I want to say a couple of words about how this might relate to the Hasegawa-Wakatani model that many people here are interested in. So let's start with a model problem, a simple scalar equation for a variable u. It's first order in time, but fourth order in space. There is a bistable nonlinearity f of u. So by bistable, I mean that there is a destabilizing contribution, something like u squared, for example, and then there is a stabilizing contribution like minus u cubed. So that equation with the quadratic cubic terms, I'm going to call SH23, and we will meet a similar equation, SH35, later in the talk. So the important thing about this equation is that aside from being fourth order in space, which is essential for what I'm going to talk about, it has an intrinsic length scale, and that length scale is given by 2 pi over QC. QC is the wave number at onset of a pattern forming instability in this problem. And there's a parameter, which is called R here, which is going to be, my bifurcation parameter, and you can think of it as a Rayleigh number or something like that, okay? Now, this equation has some important properties, and one of those is that it is reversible in space, and by that, I mean that it's invariant under x goes to minus x, and then depending on the form of this nonlinear function f of u, there may be additional symmetries, for example, u goes to minus u in the case of a cubic quintic nonlinearity. But the dynamics of this equation are very simple. The equation has a gradient structure. That means that du by dt is given by minus this functional Frechet derivative of a energy functional, this f, which I've written explicitly down at the bottom. And this f is going to be a useful quantity because it allows us to think about what's going on in this problem in terms of something that I'm going to call the free energy of the system. And that will help us interpret the properties of this equation. Now, of course, the fluid problem that I'm going to talk about later is not a gradient system. And it does not have an energy. And yet, for reasons we'll talk about, it behaves in a similar way to this particular and much simpler problem. So what do we find when we do numerical investigations of this equation? So on the vertical axis here, in this plot, I'm plotting the L2 norm of the response of the system to the forcing that is measured by this parameter R on the horizontal axis. And there is a critical value of R, R equals 0, at which the trivial solution, which is U equals 0 in solid black here, loses stability. That's indicated by the dotted line here. And that bifurcation produces a periodic structure. And that's the red curve here. Now, the initial bifurcation is subcritical, and that would be the case in the fluid problem as well. But eventually it stabilizes at a fold here, and then it becomes stable along the upper part of the branch. So this is a situation where you have bistability between a pattern state labeled P and the trivial state here, U equals 0 in black. Now, what is interesting about this problem is that on the infinite line, this primary bifurcation at R equals 0 doesn't produce only a pattern state, like a convection state, but it also generates two branches of spatial localized structures. And I'm calling these L0 and L pi, and they're also subcritical and also unstable initially. But if you follow them numerically through numerical continuation, you find that they enter this shaded region. I'm going to refer to this as the snaking or pinning region, in which they start to oscillate back and forth across this this region. And as they do so, the localized structure adds wavelengths on each side, gradually growing in extent. And L0 has a peak in the middle. These are both symmetric structures with respect to x goes to minus x. L0 has a peak in the middle, and then at the next fold along here, over here, it adds a peak on each side, so it now has 3 peaks. And then you follow that further around, and that has 5 peaks, and so on and so forth, okay? L pi, on the other hand, has a dip in the middle, so it has 2 peaks. And then as you follow that around, you add a peak on each side, so you have 4 peaks, 6 peaks, and so on and so forth. And in addition, there are these asymmetric structures, which are not left-right symmetric along these horizontal branches shown in dotted, because these asymmetric states are all unstable. And so we've called this structure the snakes and ladders structure of the snaking region. And this we will see in the fluid, the Navier-Stokes problem that I'm going to describe in a moment. But before, I was told to make this a little bit pedagogical, so I would like to explain to you why this structure might be expected in these types of problems. So let's look first at the primary bifurcation. That was that multiple bifurcation that created both the periodic and the localized states. So how do we do that? Well, we're going to look in the vicinity of U equals 0. So we're going to linearize the equation. And the linear problem is just shown here at the top. So that's a very simple equation. And the classical way of trying to predict the onset of pattern forming instability is to look for solutions that grow with some growth rate sigma. There's some wave number q. And then, of course, if the growth rate, which is a function of q, is positive, perturbations with that wave number will grow, and you might expect to generate a periodic state with that wave number. So the boundary between this pattern forming instability and the stability of U equals 0 is just determined by this condition U equals 0. Excuse me, sigma equals 0. And so that's plotted here in the lower left panel. On the vertical axis is this parameter R that I'm varying. On the horizontal axis is the wave number Q. And as I increase R, you see that there is a critical value of R indicated by this red dot. It corresponds to R equals 0 here, at which an instability with the onset wave number QC first appears. And then, of course, if I increase R some more, there's going to be a band of wave numbers that become unstable. Okay, so that's the classical way of looking at many fluid problems. But I would like to take a different perspective here, and that is I would like to look at stationary, meaning steady, time-independent solutions. And of course, in this linear problem, the only time that I have time-independent solutions is if I put the time derivative equal to 0, and then I have to lie on this neutral stability curve, sigma equals 0. Okay, so at this value of R, for example, this is a stationary solution, and this is a stationary solution. If I decrease R towards the threshold for the onset of instability, you see that these blue dots come together and they coalesce at the red dot. So looking at this from a spatial perspective, not a temporal perspective, but a spatial perspective, this red dot corresponds to the coalescence of two wave numbers at the minimum of this curve sigma equals 0. So what does this look like in the complex eigenvalue plane, where I'm going to look for solutions that vary in space as e to the lambda x, where lambda can be complex? Well, when R is positive, so I'm up here, for example, I have two real wave numbers, Q minus, Q plus. So these correspond to these crosses here, Q plus, Q minus, or IQ plus and IQ minus, and of course the complex conjugate down here. So that's the structure of the problem when R is greater than 0. And then as R decreases to 0, these two blue dots come together, they coalesce at the red dot, and that corresponds to this multiple eigenvalue here, plus or minus IQC. And then when I go below the red dot, these eigenvalues split and move off into the complex plane. So you will recognize this, this has all the signatures of a Krein collision. But here it's not necessarily due to the Hamiltonian nature of this problem, even though this is in fact a Hamiltonian problem in space. But it's really a consequence of the spatial reversibility, x goes to minus x. But the important for our purposes is that when you go below this red dot, in other words, when you're in the subcritical regime, you have spatial eigenvalues with non-zero a real part, and that means you have both stable eigenvalues and unstable eigenvalues in space. And why is that interesting? Well, it's interesting because the stable eigenvalues allow you to approach U equals 0 towards x goes to minus infinity, and also towards x goes to plus infinity, right? So this goes like e to the lambda x, this goes like e to the minus lambda x. And so that's the behavior that you would like to have for the presence of localized structures. And then the task really is to see whether these curves can intersect somewhere here due to nonlinear terms and generate a localized structure that would start off from 0 at minus infinity, do something, and then return to U equals 0 at plus infinity. So that would be a localized solution. And it's not difficult to do that using multiple timescale methods. Take U, and we're going to expand it in a series in powers of epsilon, where I'm going to relate epsilon to how far below critical, below R equals 0 I am. So that's given by this expression. And then I allow U1 to have this form of an envelope function that varies slowly in space. That's because the real part of lambda is close to 0. So the profiles grow slowly in space when I'm just weakly subcritical. And then, of course, it's multiplied by the carrier wave number e to the QCx. So this is a standard kind of ansatz. And if you carry out the calculations, you end up with this equation shown at the bottom. So this is a nice equation. I repeat it here on the next page because it has two types of solutions. It has solutions where the amplitude capital Z is constant, it's independent of X. And that, of course, corresponds to a periodic pattern for U. And so a periodic pattern, it has a certain amplitude, goes like the square root of R. The wave number is QC, and then there's an arbitrary phase because the periodic pattern can be translated horizontally. Now, there's also a localized solution, which has a Sech-like profile, and that corresponds to U of X, has an amplitude again that goes like R to the 1/2, but the width of the Sech also depends on R. And then there is this wave number QC, and then there is a phase. Now, in this second solution, of course, this is a localized solution, but because of the variation of the envelope function with space, this phase phi is no longer arbitrary because, I cannot translate the periodic pattern with respect to the envelope arbitrarily. There are only certain values of phi that are permitted because of the variation of the envelope of the solution. And there's a picture here that to illustrate that. So on the left, I have SH23, that's the quadratic cubic version of my problem. And then in this phi variable, you can actually construct a flow in phi due to exponentially small terms. And that flow has two fixed points at phi equals 0 and at phi equals pi. So there are two solutions that are permitted. But to find that out, you really have to go to beyond all orders in this kind of perturbation theory. And I'm not going to talk about that here. If you do this for the cubic quintic case, you find that there are 4 values of phi, which correspond to fixed points of the evolution in this phase phi. And so that is the situation that arises in the cubic quintic case. So what does that mean? Well, here is the corresponding results for the 3-5 Swift-Homburg equation. That's the cubic quintic equation. It looks formally very similar. Again, you have a bifurcation to a subcritical periodic pattern, bifurcation to localized states. But now you have it again looks like there are 2 branches, but the branch L0 and L pi is actually the same branch because the L pi solutions, the ones with the dip in the middle, are just the negative of the L0 solutions. So you have one branch of these even solutions, left-right symmetric solutions, and then you have another branch of the L solutions with phi pi over 2 or 3 pi over 2, and they are these anti-symmetric solutions. So it's a solution like this, and then it's mirror image under X, which looks like this. And of course, they are related by symmetry, so they lie on the same branch. So that's the structure of the bifurcation diagram for this case. Now, why does this happen? Well, to understand this, we can think in terms of an analogy with what's called phase order phase transitions. So if you imagine thinking about the gas-liquid phase transition, if you're below the critical temperature, then the liquid phase has the lowest energy. The gas has a higher energy, right? For T greater than the critical temperature, it's the other way around. The preferred state, the lowest energy state, is the gas state. And then at the critical temperature, L and G, the liquid and the gas have the same free energy, right? So that's something that you all know. This is what it looks like, for example, for a van der Waals gas. So I'm showing here for a particular temperature, the pressure on the vertical axis and the volume on the horizontal axis. So over here, I have the gas, and if I follow this branch, compressing the system, well, you might say, well, I'm going to just follow this curve all the way up to here, and then I'm going to fall off here to the liquid phase, continue up here as I keep compressing. Or if I reverse the process, I'm going to go all the way down to here and then go this way, right? So I have bistability here between the liquid and the gas, but we all know that this doesn't happen, right? Because there are fluctuations in the system. And in fact, here, I reached a situation when the gas phase and the liquid phase has the same free energy, and I have this phase transition that washes out the hysteresis loop, right? So that's an effect of finite temperature. It leads to this famous so-called Maxwell construction, where I have a transition at fixed equal energy between the gas phase and the liquid phase, and the area over here is the same as the area down here, and that's the so-called equal area construction that was discovered by Maxwell a long time ago. So the Maxwell point plays an important role in first order phase transitions, and it also plays an important role in the present problem, because if I calculate that free energy F for the periodic state, I find that it becomes equal to the free energy of the trivial solution u equals 0 at some particular value of r inside that hysteresis loop that we talked about. And so that occurs over here. So why is that interesting? Well, the argument is really this. If I have a localized state that consists of a front connecting a homogeneous state to another homogeneous state, so think of the vertical axis, for example, as density. So this would be the gas phase, this would be the liquid phase. So I have a little bubble a drop of a liquid inside the gas. And that is a stable solution if I'm at the critical temperature. If I change the temperature, for example, I increase it, then this front here is going to move to the right and the drop will evaporate. If I decrease the temperature, then the drop will grow via condensation and the front will travel in the opposite direction. So the only time I get a stationary localized solution of this type is at a particular value of the parameter. That's the critical temperature in this example, okay? But in our problem, the phase transition is different. It's a transition between a homogeneous state, think of that as a liquid, and a crystalline state, right? A state that has intrinsic or internal structure that comes from that wave number QC that we talked about already. And this internal structure means that this front is not free to move as soon as I vary the temperature away from the critical temperature. It is pinned to the oscillations behind it. And that was an idea that goes back to Yves Poumon and has been applied to many problems of this type since then. So this means that you're going to get localized structures of this type, not only at the critical temperature, the Maxwell temperature, but also in an interval around that temperature. And you're going to have to change the temperature by a finite amount in order, for example, for this front to move to the left and have a growth of the crystal from a supercooled liquid.
Could I bug you with a question?
Please, please.
I mean, apart from the presence of QC, the story that you've told so far could be said of the, I would say, much simpler Fitzhugh-Nagumo model. Would you agree, or that these, apart from the oscillatory, the presence of the QC scale, that these are, the dynamics of these are very similar?
Well, it depends. I mean, the Fitzhugh-Nagumo equation, of course, has many different regimes, but you do get localized solutions to reaction diffusion problems.
Yeah, exactly. And a Maxwell construction and an eigenvalue for the domain wall sitting there, et cetera, et cetera. The story is very similar to what you've just been through.
Absolutely. I mean, the important thing is that it's an equation for two variables. You know, you have an activator and an inhibitor, and so it's a fourth order problem in space.
I mean, usually, you know the story. Usually what happens is the two variables have different time scales. So then you look at the behavior of one variable with the other one essentially fixed, and then you go to bring in the slow dependence. And I would say the one variable problem becomes very similar to your system.
Yeah. Okay. So I mean, so you're thinking in terms of alkalines and moving alkalines and
Right.
so on.
Right.
So that, of course, relies on, you know, having this multiple time scale property. So here I don't need any of that. Okay. Right. The important thing is that, you know, I have this degenerate bifurcation in space, you know, which I can analyze completely. And that tells me that, you know, that gives rise to these localized structures, then I can follow them in parameter space and then find, you know, what they do, you know, can they become stable and so on and so forth. Okay.
Okay.
So it's a different way of thinking about these problems. They're both ways of thinking about this are, you know, of course, fine, absolutely fine. But I find this spatial approach actually more instructive. Mm-hmm. Because ultimately I'm going to be interested in you know, time-independent solutions. So let me just say, so, you know, so what we've just talked about is why the Maxwell point has been kind of unfolded, if I can use that word, by this pinning effect due to the locking of the fronts to the oscillations behind them. Okay. And so you get a whole interval of localized structures that are kind of born in this Maxwell point. So let's say a couple of words about what happens outside this shaded region. So here I'm looking at the right of that shaded region. There, the periodic state has lower energy than the U=0 state. And so you find time-dependent evolution, whereby I nucleate a wavelength periodically in time as the system approaches the lower energy state, in this case, the periodic state. And one can compute the time between these nucleation events via a method I'm not going to describe, but it works very well compared with numerical simulations. And if you go to the other side, then of course the lowest energy state is the U=0 state. And so the structure gets eroded over time until it collapses to U=0. So that's the dynamical behavior outside of that shaded region where you have stable localized solutions. A couple of things about symmetries of these problems, because that will become important in a moment. In the 2-3 case, I just have the left-right symmetry I've already mentioned, plus translations. But in the 3-5 case, I have an extra symmetry, and that is U goes to -U. So I'm going to call R1 the symmetry X goes to -X. R2 is going to be the symmetry where U is changed to -U. So the fact that you have this extra reflection symmetry means that these anti-symmetric states that we talked about, the L⁴/2 states, for example, that those are also stationary solutions of the problem. So that's an important observation. We'll see that in a moment. So just to compare the 2-3 case and the 3-5 cases, you have this kind of snaking behavior. If you go from this fold to the next one, you've added one wavelength on each side. In this 3-5 case, it's a little bit different. When you go from this fold to the next one, you've added half a wavelength on each side. And the reason I dwell on this is because in convection with Boussinesque symmetry, in other words, with midplane reflection symmetry, you're in this state. It's like the 3-5 case. The system has reflection symmetry, U goes to minus U. And so each time you go past a fold, you're going to add one roll on each side, not a whole wavelength on each side. Okay, so enough, so enough of that. So let's talk about a fluid problem. And I'm going to talk about these localized solutions that we've been calling convectons. So these are stable solutions of some PDEs, which I'm going to describe on the next page. And the important thing here is that for the same value of all the parameters, you have multiple stable solutions. And I've shown an example of what I'm calling an odd convecton, where I have a rising plume on the right, descending plume on the left, and an even convecton where the same thing happens at both sides. So the important thing is that I have multiplicity of localized solutions, coexistence of localized solutions in a parameter regime. So that's just like what we saw in the Swift-Homburg example. So what are the equations? Well, many of you know about convection here. So in convection, I'm going to use the Boussinesque approximation. I'm going to expand the density of the fluid to first order in the temperature and in the concentration. So I'm going to be talking about mixtures of a fluid. Think of salt water mixtures, but people also look at alcohol water mixtures. There are various systems that people have used for experiments. So C is going to be the concentration of the heavier component of the mixture, okay? Now, if I have a mixture and I put it into a temperature gradient, then the mixture tends to separate. And that mass flux, the mass current, that's called J here, well, there has two contributions. There is a contribution due to the usual diffusion of the concentration, grad C, but there's also a contribution to the mass current due to the temperature gradient. And the coefficient of this term is proportional to the so-called Sorey effect. And I'm going to be interested in non-zero values of this Sorey effect, and therefore the situation where I have this natural separation of the heavier and lighter components of the mixture in an imposed temperature gradient. And I'm going to be thinking about a situation where I have a horizontal layer. I'm going to heat it from below. And then the question is, how does the separation work? Now, usually, the Sorey effect is positive. That's called the normal Sorey effect. And that means that the heavier component migrates towards the cold boundary. That would be the top boundary. So in this case, if I'm heating from below, that adds negative buoyancy to the thermal negative buoyancy. And that is a problem that looks very much like standard convection. The case I'm interested in here is going to be S negative, the Sorey coefficient negative, or anomalous Sorey effect, where the heavier component migrates towards the hot boundary, which is the low boundary. And that sets up a competition then between the stabilizing concentration gradient that develops in response to the applied temperature gradient and the destabilizing effect of the temperature gradient itself. And that competition allows for oscillatory onset of an instability of the conduction state. Now in gases, there is another important effect. It's called the Dufour effect that quantifies a similar process, but it has to do with the heat flux that is generated in response to a concentration gradient. And both of these are in general non-zero, and they can be computed analytically for dilute gases via basically a Chapman-Enskog kind of procedure. But in liquids, these things have to be measured. because these are strongly coupled systems. So here are the equations. They've been non-dimensionalized in the usual way with respect to the thermal diffusion timescale. So the top equation is just Navier-Stokes. There's a pressure gradient, there's a buoyancy term here, and there's viscous diffusion. I have an equation for the temperature fluctuation around the conduction state. So that's defined here. And I have an equation for something I'll call eta, and eta is a convenient parameter to introduce here. It's given by theta minus the fluctuation of the concentration about a linear gradient set up by this cross-diffusion effect. And the reason I do that is because the boundary conditions have to be imposed on eta. Eta is, the gradient of eta is proportional to the mass flux. And of course, if I have boundaries, then no mass, no concentration passes through the boundary. And so d eta by dz has to vanish on the boundaries. So the parameters are the usual Prandtl number, diffusion ratio, inverse Lewis number, tau, a Rayleigh number, and then a measure of the Sorey effect through this separation ratio S that you see here in the equations. Okay, and the boundary conditions at the top and bottom are that the velocity is 0 there, I have no slip boundaries, fixed temperature, meaning that I have thermally, well-conducting boundaries, and that this mass flux has to vanish there, okay? And we're going to be interested in the situation tau is less than 1 and S is less than 0. Remember, S less than 0 means the heavier component migrates towards the lower warm boundary, and the tau less than 1 is required to get that hysteresis loop, the subcritical instability. And the reason is that if I introduce a finite perturbation into the system, I'm going to mix up the concentration, and that concentration will, the absence of that concentration gradient will mean that the solution is less stable. I'm reducing the stabilizing effect of the concentration gradient. And so I can maintain a non-trivial state even in situations where I'm below the onset of linear instability. So that is the role played by this tau parameter. There are some symmetries, and I'm calling them R1, R2, because they are completely analogous to the symmetries that we saw in the Swift-Homburg equation. So one is the left-right symmetry, and then there's the up-down symmetry, or the mid-plane reflection symmetry. And this means that I can get solutions that are even in space, or that are antisymmetric in space. In other words, I have to do x goes to minus x, u goes to minus u. That's the idea, right? So completely analogous to what we saw in that simpler problem. So let's do some numerical integration of the system. So I've picked some parameter values. This is essentially a salt water mixture, Prandtl number around 6, tau around 100. In large domain, gamma is 60, and a certain negative separation ratio. Okay, so these are actually experimental parameter values. And what you see here is that the initial instability is an oscillatory instability. It's a Hopf bifurcation, but it's in an extended domain. So it generates this state of spatial temporal chaos down here. Over time, as you integrate forwards in time, you see that there is a focusing instability where the activity focuses into a certain region of the domain, and the activity elsewhere is suppressed. But I'm here in a situation where I don't actually have stationary or stable localized solutions. And so over time, the structure erodes, just like we saw in the Swift-Homburg equation. It collapses back into this state of spatial temporal chaos. And then the process repeats, right? Because this spatial temporal chaos is again unstable to this kind of focusing instability. And that gives rise to these relaxation oscillations. where, here I have that gradual erosion of that slug of convection. It collapses into this chaotic state, focusing instability, gradual erosion again, collapses into the chaotic state. So this is almost, Fitsunagumo-like, and so on, okay? So you get this irregular relaxation oscillation that arises out of this process. Now, if I change the parameter just a little bit from 1774 to 1775, the focusing, of course, still occurs, but now this solution remains stable for all time, or at least until you turn until you stop the calculation. Okay, so now I've created a localized stationary solution that is stable out of this relaxation oscillation. And this is what the bifurcation diagram looks like. Here is the onset of the oscillation. That's the Hopf bifurcation. The that steady state bifurcation, it is very far out in Rayleigh number. It could in fact be at infinity. And it produces a periodic state, which is unstable here. It remains unstable up to this point here, and then it requires stability. So SOC stands for stationary overturning convection. This Hopf bifurcation generates a subcritical traveling wave, which stabilizes here at the end, this overturning convection state. And it also generates this chaotic state that I indicated already. And this represents the time average of the heat flux due to the state in this Nusselt number, Rayleigh number diagram. Okay. And the relaxation oscillations we talked about are just over here. And then when I change the Rayleigh number a little bit, I enter this region where I had those stable localized solutions that we saw. Okay, so let me say a few words about these solutions. So I've taken them apart. So I have the branch of odd solutions, those are the anti-symmetric ones, and the even ones here. And I'm going to compare what happens at successive folds as I go around this snaking structure. So for the odd states, when I go from right to left, back to right, you see that these are odd states. So I have a counterclockwise roll here. I have a counterclockwise roll on the other side as well. And this one entrains the heavier material from below. These are contours of concentration here. And so it mixes into the structure, the heavier component, and here it mixes in the lighter component on the other side. And when I go from A to C, that's the point above A, I've added a roll on each side because the rolls turn in the other direction. So now on the right, I entrain from above, and on the left, I entrain from below. And so you have transport of concentration in the opposite direction. And you can see that in the slight slope in the background concentration graph. So these things are little pumps, they take stuff from one direction, pump it across the structure, and deposit it on the other side. And the direction of pumping changes from fold to fold to fold. In the even case, of course, the rolls on the two sides rotate in the opposite direction. So I either entrain from below on both sides or from above on both sides. And you can see that in the average concentration within this even localized states. It's higher here than the average here. It's lower than the average over here. Now I wanted to say a few words about stability, because the interesting thing is these things connect to the conduction state, but the conduction state is actually unstable because it's unstable to these oscillations. And you might ask, how is it possible that the structure is stable when it connects to an unstable state in the tail? And that is related to the notion of absolute or convective instability to absolute instability transition. And just to remind you how that goes, this is a well-known thing in plasma physics, of course. If I have a convective instability, then a growing structure is advected downstream faster than it can grow. Whereas if I have an absolute instability, then the structure is advected downstream, but expands more rapidly upstream. And so it grows in the upstream direction as well. And this transition is related to a double root of the dispersion relation in the complex K plane. I don't want to get into that, but this is something that's probably well known to everybody here. And so we have computed that. And this is what gives rise to this dashed line over here. Here, the instability of the background generates traveling waves. The traveling waves propagate, but they collide with these localized solutions here. And the growing traveling waves are killed off by the collision with these localized states. And so no instability develops in the tail of these localized structures. If you go beyond the absolute instability threshold, then of course the gaps between the localized states fill in with waves. And so I'm just showing here the calculation here. You're looking at a double root of the dispersion relation, and that occurs somewhere around here. And associated with that, you have an imaginary wave number, you have a real wave number. So the real wave number is the spatial oscillation. This gives rise to the shape of the front, and it's associated with a particular frequency. And this is, what you see in experiments. These are experiments by Paul Kolodner on an annulus filled with a water alcohol mixture. These are the parameters. Here's a localized solution. And then in the background, you have these waves. And so I would conjecture that in this experiment, he's in a parameter regime where the localized states exist in a regime beyond this absolute instability threshold. And you can see states, as a function of time vertically of different widths, just as we saw in the calculations. There's another state that I think is worth mentioning, and that is that there is a traveling pulse. So this is a quasi-periodic solution in general that propagates. And of course, so that's the envelope propagates, but the peaks propagate through the envelope. So you have two distinct wave numbers, and these periodic traveling pulses are shown here, computed by the Nishiura group, and it's not clear how they relate to the stationary states that I'll be talking about, but they occur in a similar parameter regime, as you can see here. And this is what one of these periodic traveling pulses looks like in the frame of the pulse. So the pulse is stationary, and you can see the peaks traveling through the envelope in this backward direction. And then you can have more complicated dynamics as well. Now, I do want to say a couple of things. I'm going to skip this because it'll take too long. There's a comparison between the periodic boundary conditions in the horizontal and what I call insulating closed container boundary conditions. In other words, a box. And the snaking behavior with the periodic boundary conditions is very different from what you see in a closed box. And the reason is primarily because of this pumping effect that we saw. You can see here that the even and the odd states behave differently in the periodic case. In the case where I have a closed box, you can set up through this pumping effect different concentration levels on either side of the solution, and that changes the structure of this region. And it also gives you a continuous transition from the primary bifurcation through the snaking region to a domain filling state. Here, of course, there is no periodic state, and so you don't get secondary bifurcations at which the localized solutions terminate on a periodic state, because there is no periodic state. So I'm going to skip a few slides now because I want to just mention the role of the domain size. If I have a localized solution, you know, and I calculated, you know, in a small domain relatively or in a large domain, they look essentially identical. So these structures are well localized, and the reason they are localized is because they dig a hole in the concentration gradient, in the concentration distribution via this mixing effect that I talked about. Essentially gradient expulsion from regions of closed streamlines. If I go outside of the pinning region, that snaking region where the localized states exist, I get this time-dependent nucleation of wavelengths. And if I showed you this kind of plot, you could not tell, you know, this didn't come from Swift-Homburg, but in fact, it comes from Navier-Stokes. So this, you know, the Swift-Homburg works very well. And I want to show you that it also works for other things in the remainder of this talk. In 3D, things are more complicated. This is a top view of a cylinder. These structures never settle down and move around in a complicated way. I don't want to talk more about this. So let's talk about how to get these structures to move. Now, a nice way to do this, which you can do in experiments, to get them to move is to take your Swift-Homburg model, the 3-5 model, and add a non-gradient term like this. So this term breaks the gradient structure, and at the same time, it breaks the U goes to minus U symmetry. Now remember, the U goes to minus U symmetry was responsible for the fact that antisymmetric states were stationary. I've broken the symmetry that made those states stationary. So now I expect those states to drift, and they do drift. The bifurcation diagram becomes a little more complicated. The even states split into two branches of even states when I make epsilon non-zero, and I get branches here that is a reconnection between the rung states and the antisymmetric branch. So I'm going to call this the S branch. I'm going to call this the Z branch. So through these reconnections, I generate lots of coexisting, stable, moving structures. They lie on this branch, on this branch, on this branch. So I have a lot of choice of these moving structures, and therefore I can undergo collisions. And this just shows that if I look at this solution here, then corresponding to that, I have a non-zero drift velocity indicated over here, okay? So that's just to convince you that these things really do move. And here is a picture of collision of two localized solutions moving towards each other, head-on collision, time increases upwards, they come together, they coalesce into this stationary solution. So these are, very sticky collisions. This is not a, integrable PDE system. Here's a collision between two distinct states, a slower moving, fatter state, a more nimble, thinner state. This is what I'm calling a repulsive interaction, because the fronts here are like the behavior here and here from the profile are the same, and that corresponds to a repulsion between the states. Here is a follow-on collision that ultimately results in a moving a single moving localized structure. Here I have an attractive collision where the front here is the opposite to one over here. And this is a collision between a moving and a stationary state, creating a stationary state. Here's one of these repulsive collisions with a stationary localized solution that ends up giving you a moving larger localized solution, right? So this is what Swift-Homburg would predict if you break the U goes to minus U symmetry. Now, of course, we can do that in the binary fluid mixture also by breaking that midplane reflection symmetry. And the way we do that is by allowing heat to leak out from, for example, the top boundary at z = 1. So this parameter beta, that comes from linearizing Newton's law of cooling, and it will quantify, how much heat is allowed to leak through the upper boundary of the system. So that plays, that breaks the U goes to minus U symmetry in the same way as in the Swift-Homburg example. You have to redefine a little bit the Rayleigh number because, the temperatures that are fixed outside the boundaries. And then due to motion, the temperature at the top of the liquid and the bottom of the liquid, they change in response to the motion. And that's in effect quantified via some quantities called Biot numbers and gives you a slightly modified Rayleigh number indicated over here. But that's a detail for our purposes. So here, is what happens if I solve the problem with beta = 1. So that's still retaining the midplane reflection symmetry, top and bottom. So theta is fixed, is 0 at the top, just like at the bottom. And then you get exactly the stuff you saw in the Swift-Homburg equation. You have these run states which drift. They drift because it's a non-gradient system. And the picture here shows the speed. If I allow some heat to leak out, so beta is less than 1, then you get the Z branches and you get the S branches. And of course, the even branches split a little bit, exactly as in the Swift-Homburg example, okay? So that means you can generate lots of moving convectons now, and you can do these kind of collision experiments, numerical experiments. So let me describe that. So here is a nice here's a nice traveling solution. Traveling to the left, time increases upwards. So this is a state that's on one of these S or Z branches created from the branch of anti-symmetric localized solutions when I break the midplane reflection symmetry. Of course, the even solutions don't care about any heat loss from the upper boundary, and so they remain stationary exactly as before. Well, here's a collision of two like solutions at T = 0. This is the initial condition over here. This is the temperature fluctuation. This is the concentration. So you can see that these things are traveling towards each other, and then they approach each other. They glue and generate, a stationary localized solution. Of course, this is a non-gradient system, so you get a lot of radiation of waves that comes about through this collision. But the ultimate state is very similar to what you saw in the Swift-Homburg equation. Here is a collision between a stationary solution and a moving state. This is one of these attractive interactions with the opposite shape of the profile. Here, it's an asymmetrical collision, lots of radiation. Ultimately, again, a stationary localized state. Here, I have a repulsive interaction between a stationary state and a moving state. You can see that the stationary state is being pushed away. Again, asymmetric collision, lots of waves, but ultimately you end up with a localized solution. And you can, there are many more things like this. So I'm almost to the end. If I can have a couple more minutes, I'll be done. So we saw here that the Swift-Homburg equation worked very well as a kind of qualitative model for what happens in a much more complicated system, a non-gradient system, described by Navier-Stokes equation coupled to equations for the advection and diffusion of temperature and concentration. Now, in that problem, I could not derive the Swift-Homburg equation. There is no systematic regime that would generate this equation. But I know of one example, and actually it's the only example I know of, where I can derive the Swift-Homburg equation in these kinds of problems. And in the last few slides, I'd like to show you how to do that. I can only do that in the case where the separation ratio is positive. So remember, this is the case where the concentration aids the destabilizing effect of the temperature, because the heavier component migrates towards the cold upper boundary of the layer. Okay, so I'm going to impose boundary condition at z equals 1, z equals -1. It's just for convenience. Temperature is going to be fixed at top and bottom. But the important thing is that I have these zero mass flux boundary condition on top and bottom. That makes this problem look much like the problem of standard Bénard convection, but with insulating boundaries at top and bottom. And it's known for that in that case, the onset wave number is 0. And so I'm going to use the onset wave number as an expansion parameter. So the calculation I'm going to do, you know, it may look to you like a weakly nonlinear calculation. It is not a weakly nonlinear calculation. It's fully nonlinear, but it works because I'm assuming that the wave number is close to 0. So the idea is to introduce that wave number through this epsilon. There is a corresponding time scale, slow time scale. And then I'm going to be close to some threshold R0, which I don't know at this point, okay? So this is where the assumption that I have a large scale pattern comes about. And I'm going to scale psi. I'm going to work in terms of stream function here. And so that's going to be of order epsilon, the temperature fluctuations order epsilon squared. And then this eta parameter is going to be of order 1, okay, order 1. So this is not a weakly nonlinear theory. So I'm going to put that into the equations. I get a mess. The important thing for our purposes is this last equation. That's the equation for that eta. And there is an unbalanced term here with no epsilons. And so at leading order, the second derivative of phi with respect to z has to vanish. And that's, and you have to solve that with d phi dz equals 0 on the boundaries. And so that tells you that the leading order in phi is just going to be independent of z. Okay. So this is what I'm doing over here. So phi 0 is some function of x only, the slow spatial variable, slow time. Then I solve for psi naught. That does depend on z through some polynomial dependence on z. Similarly for theta. I get this equation for the correction of phi 2. Remember, phi naught is just this. Phi 2 is given by this. If I integrate this over the layer, that gives me an expression for the onset of instability. This k equals 0 instability. So that determines R0. And then I continue, and I find that at order epsilon to the 4th, I get this equation here. Now, this equation you will all recognize. If I were to write it in terms of f primed equals phi, this is in fact the Cahn-Hilliard equation. And so you end up with Cahn-Hilliard dynamics near onset. Now, what is interesting is that this parameter here, you know, by varying the separation ratio S, this can be made to go through 0. And so there's a critical value of S for that, S0, which can be computed from this analysis. And I can look near that value and then repeating the calculation to order 6 in epsilon. I'm not going to do that here. You end up with this equation here. And the nice thing about this equation, again, if I rewrite it in terms of this quantity phi, which is f primed, what do I get? Well, this is the Swift-Homburg equation, but it's the conserved form of the Swift-Homburg equation because there is this Laplacian in front. And of course, that's expected because, you know, we are conserving the mass. I mean, the mass, you know, is just being moved around by the motion. And so you end up with this conserved Swift-Homburg equation. And what this equation describes is what happens in the vicinity of the transition from k equals 0 here to a finite k at onset. In other words, from a neutral stability curve that looks like this, with a minimum at k equals 0, to a curve like this that has a minimum at small k, but not 0k. So in this regime, this conserved Swift-Homburg equation describes the dynamics. And this, this is an interesting equation. The snaking is similar to what we saw, but is slanted. I just give a reference to a paper that we wrote studying this equation. Now, this is one of the very few examples that I know that you can take Navier-Stokes and get this kind of simplified system that exhibits localized solutions. It might be interesting to think about doing some similar calculations for some of the plasma problems that people in the audience are interested in. But I would need some help from the participants here to understand the papers that I've been trying to read on the Hasegawa-Wakatani model. I have various questions about this, and not having a background in in these kinds of models, it will be helpful to me to get some help with understanding these papers and the approximations that are being made there. So in summary, I've shown you that this Swift-Homburg equation is very useful for trying to understand dynamics associated with the presence of bistability in systems that exhibit a subcritical instability, subcritical steady-state instability. We saw that that was true not only for understanding the properties of the localized solutions, but the steady localized solutions that you find, but even for moving structures where you might have thought that the Swift-Homburg equation would not be useful. I've shown you that you can get interesting dynamics arising from collisions of these localized states. They are well described by the Swift-Homburg equation, at least qualitatively. And finally, I showed you that there is at least one regime where you can actually derive a Swift-Homburg equation directly from the Navier-Stokes equation. So let me, with this, I would like to end this talk, and I would be very happy to answer questions.
Great, thank you, Edgar, for a very nice talk. Questions, if you've got a question, please just raise your hand in the chat. Xavier, please.
Well, thanks for the talk. It was interesting. I think you mentioned at the beginning the Dufour effect, which is a dependence, if I well understood, of the heat flux on the gradient of concentration.
Yes, that's
and which
correct.
I see as the Onsager symmetric of the Sorey effect, right? Which is flux versus.
Yeah, it's a symmetric. The diffusion matrix in this kind of system is a 2x2 diffusion matrix. Mm-hmm. The diagonal terms are the usual diffusion coefficients, but in general there are two off-diagonal terms. And for the liquids, like these water ethanol mixtures that I talked about, I've just kept one of these off-diagonal terms, the more important one. But in general, both terms are there. And it's well known that for gases, the Dufour effect is more important than the Sorey effect, for example.
But then if you keep only one of these coefficients, the question that came to my mind is, can you, what about the second principle? In other words, can you define an entropy there, and what does it do all along the dynamics, for instance, when you have coalescence of structures, you see?
Yeah, so the Onsager, of course, from a kind of kinetic theory point of view, you must have, you know, you must satisfy, you know, the basic properties of, you know, of thermodynamics. But I would say that here it's, you know, we are not, you know, this is a fundamentally non-equilibrium system. And so the discussion that I went through, which I hope was useful, but it could also lead to confusion about, you know, first order phase transitions. This is an argument by analogy. You know, we're dealing here with driven dissipative systems that are not in thermodynamic equilibrium, right? And so you have to be careful about, you know, about using ideas that come from equilibrium thermodynamics. I mean, it's really an argument by analogy, and I want to insist on that because, you know, this is not, you know, I'm not doing, you know, equilibrium phase transitions here.
Okay, so the dynamics, what you're saying that the dynamics of the entropy there would be meaningless because the dynamics has nothing to do with.
I think it yeah, I don't believe it has any significance.
Okay, thanks.
Pat?
Okay, I had several questions, if I may. Have you ever ventured into looking at the case in this system where the big S is negative, but where there is some noise applied in the heat? Either kind of you have a noise somewhere in the boundary or something that is at least weakly jiggling the heat flux. Does this start that kind of limit and is particularly of interest? And kind of with or without the noise, would it be fair to say in what do you see when S is negative? Do you see a situation where you have heat pulses going one way and concentration pulses going the other way?
Well, the short answer is that we have not looked at you know, forcing the, well, there are two ways, you know, you can add noise to these systems. You know, one is through, you know, imposing boundary conditions, which you know, are noisy in some way.
Right.
So you have boundary forcing, or of course you can have, you know, internal noise fluctuations in the system. We haven't looked at any of these, by the way, so I can't really answer your question. But it seems to me that, you know, the key thing about that is that the time scale of these fluctuations would have to be related to you know, some of the internal timescales of the system, right?
Of course.
Because if the noise is too fast or too slow or whatever, you know, the system will respond in some kind of adiabatic way, and I would not expect much of a difference.
Okay. Another question regards the localized structures. I mean, one, you know, people see what they want to see, but one, you know, that you describe, I mean, I think incontrovertibly, the localized structures as resulting from a mixing process. So they are, of course, a case seeming to me a splendid example of the sacred words of inhomogeneous mixing. And the question would be, is an array or a train of these things the moral equivalent of a staircase when all is said and done?
Well, yeah, absolutely. So you know, so here is an interesting problem that, as far as I know, hasn't been elucidated, either theoretically or numerically. So I showed you, the formation of a localized structure in a relatively large domain of aspect ratio 60. And you might say, and you saw that, when the system is in that state, all the heat is funneled just through one region, right?
Mm-hmm.
We're putting in heat everywhere, but it's all coming out through this localized convective structure. And so you might say, well, suppose I double the domain size. Is it still true that all the heat's going to be funneled just through one structure? And to me, it seems clear that eventually, when the domain is too big, one structure, will not be able to funnel all the heat that's being put into the system. But we know from theory that, and I didn't talk about this, is that in addition to, single pulse localized structures, we have multi-pulse localized structures.
Well, again, I mean, that's, going back to Fitzhugh Nagumo, you can have trains of pulses, right?
Exactly.
Yeah.
And the same thing is true here. And so what I expect, is that as you make the domain bigger and bigger, you're going to transfer stability from a single pulse state to a 2-pulse state to a 3-pulse state. You understand? So just so that the system.
Yeah, well, I mean, of course, we being the fusion community live in the large, and I might add, large cost domain limit. So, that's why we sort of immediately ask these kind of questions.
Yeah. So just so for these odd pulses, so if these pulses are these antisymmetric pulses, and you had an array of the antisymmetric pulses, then absolutely, you would be pumping stuff from one end, through the pulse to the next pulse, and that would, pump again. You understand? And so you would in fact have something that looks like a staircase, because you would have an overall gradient, but with these step-like structures due to the presence of these pulses.
And then with the symmetry breaking, near the end, the non-conservative term, of course, bingo, you'll have a propagating array. And then you get these things like the escalator states that we found in certain cases of sort of Bly meets Hasegawa-Wakatani and so forth.
Yeah, absolutely. And so you could get, migration of interfaces, coalescence of, right? I mean, you could interpret what I've just talked about, as describing coalescence of steps.
Okay, I might come back for more later, but
Pat, I have been trying to read some of your papers on this Hasegawa-Wakatani stuff, and so maybe offline we could at some point.
Well, I've got a better alternative, and at least maybe better for you. I'm happy to chat, but I could just, for you and anyone, like particularly students. So I gave a course in UCSD, in my living room. You'll see my cat in a few occasions on, magnetic fusion theory. And there's a ton of stuff, including all the notes and all the videos and all the references. So you can, and a lot of the things I think the questions that are bugging you are all laid out in excruciating detail. And you can turn the videos on and off at your convenience. So I send you a link to that. How's that?
Perfect. Yeah, I will look at that.
And then we can talk from there. But I mean, but don't send the link to Guillaume, or he'll start making videos ridiculing me or something like that. He's good at that. So
I'll keep it a secret. So.
Right. Okay. Speaking of Guillaume, off you go, Guillaume.
Well, that's a below the belt attack, which is totally uncalled for. Well, I would have several also, but maybe one is just a clarification. So apologies if I misunderstood and you already said it, but I'm trying to understand what sets the boundaries, the region of the pinning, because the way I understand your conductance, sorry, you have an odd and an even conductant. If I got it correctly, the odd one basically takes all the stuff and put it to the boundaries. So what prevents that structure to ever grow in space? Is it the fact that you have a superposition of odd and even, and then the even one deposits within the structure or funnels through the structure? So you get an overall equilibrium of your structure given a certain amount of heat available. So the question, if I had it correctly, is what prevents the spread of?
Yeah, so if I've understood, so first of all, so these systems have this region of bistability, right?
Mm-hmm.
The localized states are found only in a sub-region, right, of that bistability interval. Now, so you ask what determines the width of this region where these localized states are found.
Mm-hmm.
So, I mean, the simplest answer to that is, but it's not going to be helpful, is that it's the pinning effect, between the front and the oscillations, within the structure. But of course, we don't know how to compute that pinning force, right?
Mm-hmm.
But the point is, you have to overcome that pinning potential, let's call it, in order for the front, to be able to move, and therefore for the localized states to be destroyed, right, by front growth or compression.
Mm-hmm.
So it's fundamentally is determined physically by this pinning potential. So if we could calculate that, we would be able to calculate the width of the spinning region.
Yeah, this I think I somewhat understand, but I guess I'm asking, is it connected to the amount of heat available, for instance, or and you need this superposition, of this odd solution that you find and the even solution that somehow allows you to carry the heat. And if you were to increase the amount of heat that you would impose at the boundary, basically the thing should have to expand to accommodate for the forcing or something like that.
Well, I mean, of course, it depends, on the heat, because the localized states exist over an interval in Rayleigh number, right, which quantifies, the forcing, the thermal forcing of the system. Now, but fundamentally, the reason these localized states are there is because, they locally mix up the concentration, thereby reducing the stabilizing effect of the concentration and kind of, building a nest for themselves, right? They dig a hole in the concentration gradient, and then the concentration gradient confines them, right? And the Rayleigh number, its main effect is actually in determining the time scale on which that erosion process occurs, right? Because the Rayleigh number determines the velocity, and the velocity determines how rapidly, determines the Peclet number, so-called. And that determines, how efficient is the expulsion of gradients from regions of closed streamline. I'm not sure I'm answering your question, but that's the basic physics of these. And that's why these things, maintain a size even if you make the domain bigger. Mm-hmm. They don't expand.
Okay. But what do, physically, what do your odd and your even conductance do? Because the way I understood, but maybe I'm incorrect, the odd, I think, conductance basically takes everything that would be within the heat that would be channeled through the structure and takes it outside, so puts it to the boundaries. And the even one would do similar things, but through those plumes that are that cross the structure. So what's the role of having both at the same time? And
Well, so
misunderstood.
yeah, so in this what I'm calling the pinning region, where the fronts are pinned to the structure, you have multiple even solutions and multiple odd solutions of this type. Okay, so this is with periodic boundary conditions, and so this is a periodic solution, and you can see here that the structure picks up heavier component from from the bottom, and and the heavier components on the bottom because of this negative Sorey effect, and it entrains it, right, and mixes it through inside here, and then it ejects or entrains lower concentration from above, and so that generates these kind of inclined contours outside of the localized solution. So this is it's a little pump. If you make the domain bigger, it'll do exactly the same thing. It'll transfer heavier component from the right and essentially deposits it on the left. The even ones don't do this pumping. They just entrain material from both sides, and that then determines their mean kind of homogenized concentration. And of course, you can put multiple states of this type. I don't have pictures of that here, unfortunately, but you can put multiple structures like this together, and essentially they'll behave the same way. I mean, you can put odd ones that have the same orientation, and then that system would behave much like what I talked about with Pat Diamond just a moment ago. You would get a kind of staircase-like structure. Or you could have these ones, back to front, pumping in opposite directions, and then you will develop, a larger concentration between the convectons and a lower concentration on either side, right?
Okay, so I misunderstood. You don't get a superposition of both. You get either one. Okay.
That's right. These are fully nonlinear states. Yeah, there's no superposition. You either get one or you get the other.
Okay, thank you very much.
Can I just ask, Edgar, in terms of your pinning region in Rayleigh number, sometimes in some of your systems, it's remarkably invariant, like each snake turns around at the same Rayleigh number, like in your Swift-Hohenberg example, and indeed, I think in one of your binary, and in others not. Is that a reflection of the symmetry in the system somehow, or?
Well, if you have if the system is non-conserved, in other words, if there isn't a conservation law in the background, then you can show that these folds, the saddle node bifurcations, they will align in the vertical direction exponentially rapidly.
Oh, okay.
And so the first one or two are going to be off a little bit, but after that they all bang on, vertically. But if you have a system with with a conserved quantity, then the folds do not align vertically, and you get what people sometimes call slanted snaking, where the folds are always at a different Rayleigh number. And the reason for that is that in a finite domain, you have a certain amount of mass, let's call it, but it could be magnetic field or whatever, magnetic flux, that you just have to redistribute, right, in the domain. And by incorporating a lot of it in, say, in the localized structure, you have to have removed some from elsewhere, right? That's what a conservation law implies. And that means that effectively you've changed the local Rayleigh number. And that's why the folds no longer align in the vertical direction.
Okay. Okay, right, thanks. Pat? Your hand is up. again.
hand is up. It's not fossilized either. You know,
No.
my hand is not always up. So in the obvious position. I mean, I find myself always making analogies with Fitzhugh-Nagumo because that I do understand something. Notice I said something about. In that game, the size of the pulse, okay, that you get is, well, first of all, the pulse is determined by the demand that the forward domain wall is going at the same speed as the backward domain wall, right? In other words, you have a transition up and you have a flat top and you have a transition back. And what defines the pulse is that the up and the back are moving at the same speed. So everybody's going at the same rate, and that imposes an amplitude relation because the transition back depends on where it starts from, which is the amplitude. I mean, does something like that govern? Well, it's not going to be the same because these things are wiggling, you know, as opposed to flat tops. But is something like that going at work here in defining the size and also the speed of the convecton? And that was the other question, yeah. Is what's the speed of this thing when it's moving, you know?
Yeah, right. So yeah, so a number of points that I should make in response to that. So the important thing here, in fact, let me go back to my little picture here. Sorry. Which way do I want to go? This picture here. So this picture, you know, relies on the fact that the system is reversible in space. It has this symmetry x goes to minus x, and that means that whatever happens here, you know, there's a corresponding image that occurs on the other side, and there is an axis of symmetry with a horizontal derivative. And so what you have to do, you know, so if you know, the localized states I'm talking about are heteroclinic orbits connecting u equals 0 to a periodic state. Right, to get that kind of connection typically means, you know, that you have to vary, you have to pick a parameter value to get that connection. But the reversibility in space means that once you've arranged for a connection between u equals 0 and a periodic state here, you also have the backward connection. Right, that's what reversibility gives you, and it gives it to you for free. And that is heavily used in the theory of all of this behavior that I talked about here. And in particular, for example, even in the moving structures, those moving structures are stationary states in a moving frame. Now, in the Fitzhugh-Nagumo problem that was mentioned, you have moving structures, right?
Right. Or you can have. I mean, you can have stationary structures too. So.
Sure, but you talked about moving ones.
Yeah.
And the point about the moving structures is, you know, if you want to have a connection, say, from u equals 0 to a periodic state, you have to pick one parameter. But the connection back to u equals 0 is a different connection. And so you would need, in principle, to pick a second parameter to make that one work. And so that makes the moving structures codimension 2. Because you have to actually pick two parameters, one to get a connection from here to a periodic state, and then from the periodic state back to u equals 0. And notice that in the Fitzhugh-Nagumo problem, you actually don't have solutions of that type. You have just pulses. And the pulses are just homoclinics. They are not actually a pair of heteroclinics, you know, one of which connects u equals 0 to a periodic orbit, and then from a periodic orbit back to u equals 0. You actually just have pulses. And those are homoclinics. To get solutions of the type I described, which have these multiple oscillations, I believe, that's a higher codimension problem. And so by varying a single parameter, you would not expect to see those.
Mhm. Mhm. Okay, thank you.
Could I ask just one more, Edgar? So your actual simulations are 2D, presumably.
Yes, yes.
I
I
mean,
only showed one 3D, and that was this shrimp,
yeah,
call it the shrimp state. Where was it? I don't know where it was here.
I mean, are there analogous things in 3D in if you've just got the plane layer? I mean, does anything happen like this in 3D, or is it, I guess?
Yes. Well, right. So of course you can, and many studies have been made of Swift-Homburg in 2D, I mean, the plane, right?
Mhm.
And in fact, we have, so there's a lot of stuff on Swift-Homburg in 2D, and there are all kinds of different structures, different types of localized solutions. Now, we have done 3D calculations, not in this particular problem that I talked about here, but in a porous medium. And the reason for picking the porous medium problem is that the Navier-Stokes equation is, is simplified through a Darcy type equation of motion. It just makes things a little bit easier. So you just have nonlinearities in the concentration and in the temperature fields, okay? And there we find, and I don't have pictures of that here, but we find structures that are basically star shaped. They form arms, if I can just describe this in words. They form arms. For example, it depends on the domain, if it's square domain or other. But they typically form arms like this, and then you get snaking associated with the growth of the arms.
Right.
Until they hit an image, for example, if you're using periodic boundary conditions. But then you also get super snaking on top of that has to do with the closure of rings around the center. So you basically build up a circular structure with arms pointing out. And that those can be stable as far as we can tell numerically. Again, because this structure digs a hole in the concentration field and the concentration field then kind of maintains it. It's like a wall. The concentration is like a wall around the structure, and that structure is maintained and apparently can be stable. In this problem, the 3D structures that we found were all time dependent. And this thing is at two different times. The thing just moves around and is never apparently stable.
Okay, thanks. Yeah.
I'm thinking an analogy with the plasma here. To have the structure that you need, and to have the pinning, you seem to need to heavily depend on having this oscillatory solution inside the solution. Plus, you impose the negative Soré coefficient. If we were to extend it to, for instance, the staircase or whatever, I was kind of thinking what would be the analogous of those oscillations that you have in the step. What would be the step of the staircase, and do these oscillations, which probably would come from certain types of waves, would those certain type of waves give you the consistently, not imposed from the outside, the negative Soré coefficient, and in our case would give you, for instance, a negative diffusivity or negative resistivity? So I'm guessing, do you have a way to connect those oscillations within your structure to actual waves, for instance, and what would be required from those actual waves to get negative Théorie coefficient?
Well, yeah, so that's a difficult question. So, I mean, the first thing you mentioned was, the internal structure. So of course, in the staircase, in the oceans and so on, these interfaces are always turbulent anyway. So, we're not, the structures that I'm talking about are certainly not that. But the point is, you have multiple coexisting states, and that may well be true for the staircases, I don't know. Which one you see will depend on how you set up the system. And it's certainly possible that, just the simplest internal structure, say with just one row, might be the thing that, that you will see. As to waves, of course, these systems do support waves, because after all, they are self-stratifying. I mean, the concentration separates in response to the thermal gradient that's imposed. And so they do support internal waves. That's certainly true. But I don't know, I don't think these play any important role in the kinds of things I described here. I do want to mention is that the Théorie effect is not negative diffusion. It's definitely not negative diffusion. It is just an off-diagonal term in the diffusion matrix. It's very different physically, I think.
Thank you.
Right. I think we're probably done. Thank you again, Edgar. That was a very interesting talk, and thanks for answering so many questions and things.
Thanks very much.
Okay, well, thank you guys for coming, and we'll see you next week.
It's time for some water alcohol experiments, at least on this side of the Atlantic.
Right.